Good morning. This is Muhammad Ashraf once again. We covered Introduction to Six Sigma and the Define modules. Today we are going to talk about the Measure module. I hope you recall what we covered in Define. I hope you recall what you have covered in Define. So Define was basically defining the problem, getting what is your y variables, the critical to quality parameters for the customer, and then finally putting the process into a SIPOC format, which was breaking up all the activities into sub-steps the way they are executed in an orderly manner: supplier, input, process, output, and customer. So the process sits in the center with all the sub-steps, and on left there is suppliers and the inputs, and on the right is the outputs and the customers. And the way it was looking, let me get into my pointer again. So these were your outputs and these are the inputs. So today we are going to dig deep into the measure phase and see what kind of tools we are going to employ. The major activities included in the measure phase are determining the critical x's and y's. You recall we made the SIPOC, so the SIPOC is the one which is going to give us the x's, which are the inputs, and the y's, which are the outputs. We are going to determine which ones are the most important ones, and if you recall we had a Pareto analysis. We'll be using the Pareto to establish which ones are the most effective inputs which are having the effect on the outputs and start working on them. There will be determining of operational definitions, establishing performance standards, developing data collection and sampling plan, validation of measurement system analysis, determining the process capabilities and the baseline. The major quality tools used in this phase are C&D relationship, MSA, check sheet. I wouldn't say it's a tool, but it is a tracking tool, and then the process capability. What it flows overall, the activity flow in measure phase is we have the list of our x's and y's, which goes into the sampling plan. What is the sampling plan? Basically you establish which critical parameters are which you have to work on, the critical inputs, and then you start collecting their data. You start collecting their data to establish that how your system is performing now. We go into doing an MSA, which is the measurement system analysis, gauge repeatability and reproducibility analysis. We dig deep into the process capability, what our current parameters are performing at, and they will form our baseline which we want to improve. And then we go further to establish this red one would be the baseline, which is the current situation, and we want to hit the green target, which is the goal. Determining the critical x's and y's. So some of the x's, we start from the y's there, which is what the problem at customer level is being seen as: manufacturing quality, the cost of quality, cycle time, customer satisfaction, material costs. These are some of the y's, or we call them lagging, because once your system is starts operating and producing or giving the service there, you see these results after some time. They are not visible immediately. They are the effects of the system, but nevertheless they are very important, because this is what our customer is seeing. Our customer would be evaluating us on the cost of quality or the quality itself. If it's an internal customer, they will be looking at the manufacturing cost. If it's an external customer, they will be looking at the actual quality and their satisfaction, which sums into this one. Another kind of parameter may be the cycle time. Again, the customer is looking at how fast your product is being delivered, or your internal customer is looking at how much time you are taking at manufacturing. Time is money. And then the material costs there. So some of these examples are cited here, which would be measured at the output. How are they related to the inputs there? So the yield, scrap, rework, processing time, wait time, delivery, accuracy of transaction time, inventory levels, material management. These are the intermediate levels of those variables which are translating into this. And we take a step backward further. So the errors in the time, offset, viscosity, what is distinct here? These are all parameters based on individual physics, chemistry, and basic sciences of the system. So you go step by step, you translate this into this level, and then start working on these ones so that they will be affecting these, and these will in turn start affecting them. The overall story is that these outputs are never realized immediately. So that's why you have to focus on the inputs and with full diligence, so that after the cycle time or after the overall maturity cycle of the process, this thing shows up and which is in your favor. Using QFD or C&E matrix to prioritize and select project Y's and X's. You recall your SIPOC. Your SIPOC had a certain set of X's, which were the inputs, and your SIPOC had certain set of Y's, which were your outputs. So the outputs are basically the customer wants, which is what the customer wants to see. And the inputs are basically which you can control and deliver there. So the way it works is, again, due to the introductory nature of this module, I'm not going to the actual detail of this tool itself. It requires a couple of hours of training to go into this tool. But what you do is that you list the customer wants on the vertical axis, and how you are going to address how you are addressing them on the horizontal axis. And then there is a cross relationship of these matrices, of these rows and columns, and we establish them on the basis of 0, 3, 6, and 9. You relate them, 9 being the heaviest relationship, 6 being the moderate relationship, 3 being the weak relationship, and 0 being no relationship at all. What this will do is this will give you a weighted relation list of how important these wants are. A point to note is some references go by 0, 1, 3, and 9. This example which I have picked up is going by 0, 3, 6, 9, but if you face in the industry 0, 1, 3, 9, that is equally good, but there is a big discrimination between the important variables. The gap between 9 and 3 and then 1 is 9 and 3 is a big gap, which helps you to discriminate really important variables to focus on. This tool is called Quality Function Deployment, or QFD, or another name is C&E matrix. There are templates available within Excel, and there are also templates developed in other statistical analysis tools, but this is not a statistical tool, so that's why mostly we rely on Excel, and the templates are available. Performance standards for each Y. You have three possibilities there. Either the Y is to be maximized, you want to have the best larger the better. It's one-sided and there's only a lower specification. Anything which falls below the specification is unacceptable, and anything which falls above is acceptable. Smaller the better. Again, you have to minimize it now. So anything which falls below the upper spec limits is good. Anything which is falling above the spec limit is false, wrong. And then there is the two-sided specification, where you have to be between the two spec limits. A question to you guys is that where should you be playing? Should you be playing next to these limits, or should you be playing far off from these limits? If we recall our lesson there, the more further we are playing, we have a chance of any error. If we are producing in this part and on the other end, if you are producing in this part, and by chance we have an error and we go here, let me get the pen and give you example much better explain there. So if you are operating in this zone, if you are playing here, your play field is here, you are good. If by chance you produce something here, you're still good. But if you are already playing in this area and any slightest mistake, you jump into the failure zone. Likewise here, if we are working in this area, let me change the color of the pen so that we can. So if you are working in this area, you are in problem zone. You can, any mistake, you can jump over the spec limits and fall here. Like if on the contrary, if you are working in a further zone than the spec limits, you have any error, you can fall here, but still have the chance to improve and get back to your limits there. Looking at this one, it's a recall of what we studied earlier. Here's an exercise for you guys. You can do it on your own time. Read this whole passage and count the number of G's you can see. Number of letter G's. Give it one try, second try. The purpose of this exercise is to tell you how much variation is there. You can do this exercise with a friend, with one friend, with two friends, and see where do you land, what kind of answers you are getting to the number of G's there. And how you can find the correct answer? Somewhere in this slide deck there is the answer hidden, and you can try to explore that answer. If you go through each slide carefully, you will see that it is written somewhere, the actual number of G's. And you will be amazed to find that every time you read it yourself, you will find a different number. And every time you check it with another friend, you will find a different number. Your friend or you and third friend, each one will be coming up with a different number. That is the inherent way I talk about this. So I talked about this to demonstrate what happens in our actual measurement systems there. Measurement system is the key to your measure phase. If your measurement system is faltering, it may tell you that you are producing good, or you are resulting in your operation is fine. That is living in a fool's paradise or a false sense of security there. And if the measurement system is bad and you are actually producing good, again you are at loss. You are rejecting your good parts. And you might be in the two situations that you are supplying bad parts to the customer thinking them good, or you're rejecting good parts thinking that they are bad. So hence the step one in measurement phase is to establish the accuracy of your measuring system. Look at these presentations there. So this is what is the problem here. Neither you have to hit the bullseye. Neither you are accurate nor you are precise. Accurate means that you have to hit the bullseye. Precise means that you whatever you're doing, every time you're repeating the same mistake there. So had it been that all these dots were on very focused on the smallest point there, at least you know that your system is repeating. You are firing the darts on the wall, and you are hitting every time you are hitting the upper left corner, so you can adjust your aiming to this level. That is, your system is neither precise nor accurate. Let's go further. Your system here, you are able to hit the darts on the target, but they are not going to the center. So you are accurate, you can aim well, but you're not precise. You're not precise to hit the center point there. This one was the case which I talked just few seconds earlier there. You're not able to hit the target, but however, you are very precise. You can move it to this with some exercise and training. And let us come to the best case which you really want to have is accurate and precise. Your scale should be measuring 1 kilogram every time with the same accuracy, every time with the same precision. That way you have the confidence on your scale that if I place 5 kilograms, it will be telling me 5 kilograms. It will not be telling me 4.6 or 4.7. Or sometimes you measure it, it shows the 5 kilograms as 5, but sometimes it shows as 4.5, sometimes it takes to 5.5 there. We all must have experienced this situation. If the guys amongst us who are overweight like me, whenever they go to the scale and the day the scale shows a lower weight, we are very happy. Then we straight away jump onto it once again, and the scale this time shows you 170 pounds, which was 150 pounds short while ago. Now you are in a fix. You want that scale to show the correct measurement every time. So where do the measurement system variations come from? You recall this figure? What is this figure called? This kind of representation is called, we covered in our, did we cover in our, no, we will be covering in our next module, which is called Ishikawa diagram, or the fishbone diagram, or the cause and effect diagram. Whatever it is, the name you see there, it is that the output problem is listed here, and the inputs are divided into materials, men, machine, methods, environment, and the measurement type is an extra leg into this figure. But materials tell you what kind of issues are in the materials category. Men's leg tells you what kind of issues can happen in the men or human, much better to say that way, that they may be procedure, fatigue, training, speed, or however they are following the execution. That is that part. Machines, there may be machine issues, that machine is dirty or machine has worn, is not designed properly, that falls in there. Methods, what kind of processes you have laid out, those methods will be affecting the measurement error as well. And the environment also plays a critical role, that what kind of humidity, what kind of temperature is running there, which is going to affect your measurement system. So the measurement system will have some inherent variation. It's not that your measurement system can be totally variation free, but you have to keep the natural variation within its limits and not add on with unnatural variations which are coming from these sources. Why MSA? So there are multiple variations there. Your product is being produced or your service is being delivered, it has its inherent variation. You cannot produce a 10 centimeter diameter to the perfect fifth decimal every time. Sometimes it would be 10.01, sometimes it would be 9.998, but every time it cannot be a 10 on the national standards index there. You'll have to counter from some variation. So this is one kind of variation, that is the natural variation which is existing. Then there is the measurement variation. Measurement also, it has its own account of variation. You cannot deprive it of natural variation, which will be happening in every case there. Now there are two variations, but what is the overall variation which is going out? Which that is the sum of these two variation. So if these two are out of control on their own, this would be way out of control. If you are able to manage these two within the control, or even more as narrow as possible there, which depends upon your investment there. You cannot have a nano machining in your manufacturing shop when you only need a micro level machining. That's why I say it, that within the admissible limits, what your business case justifies, you keep these variations into limits that will result controlling this variation. You have control over these two variation, but you don't have control over this variation. This is the output of your product variability and the measurement variability. The notations shown here, this sigma squareness is a statistical term. The sigma is the statistical term of standard deviation, and when you square it, it shows the variance. But it is essentially the same parameter as we talked about the standard deviation. Observed process is equal to actual process plus the measurement system. Measurement system is equal to repeatability and reproducibility. Repeatability is the function of your process, that you produce the same product every time, and reproducibility is the function of your measurement system, that it measures the same thing every time. Possible sources of variation. Again, I will not spend much time onto this. It's the same repetition of the same slide which I talked about, that observed process variation. This is the actual process variation. Actual process variation might be due to the manufacturing defects or the inherent variation. You might be having a long-term variation, a short-term variation, or variation within the sample. Then the measurement system variation, it may having the variation due to the operators and variation due to the gauge. Variation due to the operators is something which we have to address. Variation due to the gauge, which is the inherent variation of the system, you have little control of that, but you have more control on this. Variation due to the operators is called the reproducibility, whereas within the variation due to the gauge, you have linearity, stability, accuracy. These three are the design and manufacturing of the measurement gauge, whereas this is the output of the operation of the measured gauge. So repeatability and reproducibility together sum up to give the overall performance of the measurement system. MSA for the measurement, for the validated measurement. So there are two concepts here: short-term capability, long-term capability. Short-term capability is that your system should be accurate and it should be repeatable and reproducible. So you measure the same part 10 times, it should be measuring the same thing. You have 10 parts which you are measuring at different times, it should be repeating the same measurement on those 10 parts because they are the essentially same parts. That is repeatability, this is reproducibility, and hitting the target is the accuracy. This is something which you have in the short term there, that is in a day or in a month. But the long term is that your system should be stable. It should not, its accuracy should not drift to another way, to the left or to the right there. Long term, if you are checking your measurement system maybe once a month and see that every month it is drifting to either right or the left of the target which you are supposed to measure there, that is something which is called calibrating your measurement system at the designed frequency. So your measurement system should be performing well in the short term and as well in the long term, that both together go in hand. If you have calibrated your system at a monthly scale and it starts differing every 15 days, that is probably either your calibration cycle is shorter, which you should mend it, or your measurement gauge is drifting. For that reason, you have controls in the place that you inspect that every predetermined frequency. Control is something which will be the last module, and we'll be talking about that there. Develop a data collection plan. Remember, in the beginning of this module we talked about X's and Y's. Y's are the variables which the customer sees, that's what you have to affect. But the variables which you are controlling, they are the X's, and they go in the system there. So this is a data-driven methodology. You remember, Six Sigma is strongly a data-driven methodology. So what you have to do, if your system is, if your process and system is not recording the data earlier, you don't have any data collection set up already in your system there, then you have a problem. If you have a data collection system already in place, you can pull out the data and see the performance of the system over time. But if you don't have a data collection system, you have to establish a data collection plan. So for all those X variables which were important for the performance of your system, you establish a data collection plan for each of them. You measure those parameters, and remember, before the data collection I covered MSA. You have to first fix your measurement system. If the measurement system is not to the standards, you cannot go to the data collection. So first you have established that your measurement system is good. Next step is move to the data collection and start collecting the data for those variables. The frequency and how much data, how many pieces you measure, what kind of data you have to collect, it all depends on what kind of process or system you're trying to improve. So you have to sit in together with the process gurus, the process leaders who are working there, and get their input that what variables with what frequency should be measured, and your C&D matrix will be dictating you in that as well. Collect visual data to see the problem. You see what I have written there, CSI. What do you think the CSI means? CSI, those who like me who are buffs of those detective series on the TV, it refers to crime scene investigation. So even your process or your system or your manufacturing line or your transactional service system, whatever it is, they are all crime scenes. Failing to meet the customer requirements or failing to meet the customer variable, which is a quality variable for them, is a crime in this world, in the world of Six Sigma, in the world of providing service to the customer, in a world of generating profit for your company, for your industry. So you have to go and start measuring at the crime scene, see what really is happening. Your documented processes, your documented systems might not give you the real picture. So start investigating from the crime scene. Wherever possible, use the digital or video camera and capture the defects and the process of the problem there. That way you can translate it back. So having talked about the X and Y variables, talked about the C&D matrix, then the measurement system analysis, and then the crime scene investigation, how do you collect the data, where you start collecting the data. Next we come the process capability. So what does the data tell you? The data will tell you a story whether your process is capable or whether your process is not capable. So there are some key values to or key terms to remember there: voice of the process, tolerance limits, process capability. So voice of the process is that what your process is doing now, where your process is functioning now. Let me get my pen once again. So your customer voice is the specifications there, that I want something in between. Now we go and change our color and etc. and again. So your process is working here, or your process is working here. So the voice of your process tells you that where I am functioning. I am functioning in this zone, or I am functioning in this zone. So you have to pay close attention to the voice of the process, that when I am functioning like that, this is I am, this is what me is. You have to pay a second focus on the requirements from the customer, which what is wrong in this picture. I think I talked about this example in my previous module also, but your garage door is way smaller than your car, so that is a big problem. What is right in this picture? Your garage door is big, your car is smaller. So either you have done two things. You have magically got a shrink ray and shrunk your car to a smaller car, or you have gone to a bigger house and got the bigger garage there. It is all depending on your business. If your business allows you to expand your garage, why not? Go ahead, do it. But if your business does not allow you to expand the garage there, you will have to invest on a shrink ray and make your car smaller so that it can go through that garage. Process is capable when it's able, with its natural variability, to meet the customer specification. The process fits in the specifications there. I will redraw this thing once again and jog your memory. Remember, these are the customer spec limits. The garage door limits are the spec limits, and what we are having here is, and your accuracy falls in this zone. Pardon my mouse drawing, it is not that accurate, but the concept is there that you have to fall within these limits. Now in this case, you have the liberty to park a little bit left or a little bit right without hurting the customer. How capable is this? It's up to you there. If you shrink the car even further to a level of a very micro car in this zone, you are free to operate in all this area. If your machines are drifting left or right there, it is what it is. You can live with it. But there is another thing to learn here, that if you shrink your car to very small car and your limits are big, what you can do? Why study the process capability? So once you have collected the data, then you map that data to see how capable your process is. That will give you the baseline. The baseline is telling you where you stand. The baseline is telling you what is the current voice of process. And then you can compare that voice of process with the voice of the customer, and that gives you the gap. What you have to do to get the improvements. So what is process capability? Again and again, we are visiting the same normal distribution histogram, the Gaussian distribution. If you remember the last or second last slide of my intro, where I spoke about the history, and the Six Sigma started the day when Gaussian distribution or normal distribution was put on the paper, and we are referring back to that again and again. There is the inherent reproducibility of the process output, measures how well the process is currently behaving with respect to its specifications there. Natural process limits, the specifications. So if your process is so wide that is going beyond the specifications, your process, the voice of the process is outside the voice of the customer, you are in trouble. But if voice of the process is within the voice of the customer, you are happy. How within, that is what is Six Sigma going to tell you. This is what Six Sigma is all about, that you have to be well, your voice of process should be well within the voice of the customer, and capability is the measure of that. We are just revisiting, we talked about this thing multiple times there. Anything which falls out of these tails is a rejection, and if these tails are wide and big, you are at the verge of losing your business. Simple as that. Parts per million, we spoke about that. Z score is something which we have not talked about that explicitly, but the numbers of the sigmas within the spec limits, that is basically the Z score. How do you get the number of Z score? It is a standard arithmetic. Specification difference divided by standard deviation gives you number of Z's, number of the standard deviations within the spec limits. That tells you how good your process is. Process capability matrix, CPK and PPK. That is something I'm going to tell you in the next slide, or in 2 more slides later. Process capability indicates the consistency of the process output. It indicates the degree of which the output meets the specification. Be used for comparison with other processes or competitors. So we talked about these first 2 items in the previous slides there. It shows how within the limits of the voice of customer you're following. The third point here is you compare it with other processes. It is a process independent metric now. Once you translate your data into process capability, you can compare the production of bearings with the production of shafts and see that which process is more capable. The production of shafts is much within the specifications and much within the voice of customer, whereas the bearings is not. You can compare both of those lines. Process capability versus specification limits. Process A is highly capable. Why? I need not tell. I leave it to you. Process within on the B is marginally capable. Again, why? I'll leave it to you. I have talked about that multiple times. And the process in C is definitely not capable. Why? I give a hint. The tails are outside the limits. Again, process specification scenarios. One is that your natural variation is within the specifications. Excellent. Your natural variation is going beyond the specifications. Very bad. Your natural variation is meeting the specification. Fair, but you are in danger zone. You have to do something. And your natural variation is, the mean of the natural variation is drifting away from the specifications. So again, your process is drifted. This situation is not good. The only good situation to live in is this one. Whenever you fall in any of these situations, you have to take a corrective action. 2 types of limits we talked about. This one is the voice of the customer. This talks about where the customer wants. I would present it again. It is the same concept in a different way, just to hammer what you need to learn here. Okay, so this one is VOP and this one is VO and a C. You tell me, is this a good case or a bad case? I think I have drawn an excellent case there when your process is always manufacturing within the limits there, and the process is showing that I am well within the customer specifications. So even if I drift left or right, there will be alarm and you can bring me back to the shape. But if this tower, this mountain expands beyond the customer limits, it is going to raise an issue there. This is the picture which you have to try to paint. On the short term basis, you can get it. On the short term basis, you can manage your process. But the good process is which performs consistently over long period. Long-term performance of process includes all assignable causes which impact the process setting. Production shift, operator, machine, tool wear, periodic maintenance schedule, breakdown, calibration, temperature, humidity. All these things change daily. So day to day these things will vary. When you are going to design or improve your process, you have to factor these. And how do you factor these? You collect the data from your system, from your process over long period. You don't just take a snapshot in the time and then say that my system is performing well. You have to demonstrate that your system is performing well over time there. Short-term performance usually represents the effects of limited noise or inputs there. Limited noise means that today everything is doing fine, you have excellent temperature and you have an excellently trained operator who is working, that is going to get you an excellent results. Comes the second shift, the temperature has changed, the environment has changed, and you have a grumpy guy who has fought at work and he is not paying attention to his work. There will be a shift in the output there. There will be shift in your results. That's what we have to factor on the long-term accuracy and long-term performance of the system. Shift will happen, we have to account for it. Again, these all the representation of Monday, Tuesday, Wednesday, Thursday, Friday. Overall, this is what the customers see. You remember in my very first module I said the customer is least concerned about your average. On the average, this process shows that you are hitting the target, you are close to the target. But what happens is the daily variation, it is going up or down, and these are the things which are being shifted to the customer. Customer will not say that your average is good. Customer will say what I am getting is bad. I am getting something good on Monday, but I am something getting awful on Friday. I am not going to do the business with you. Which metric will you be using? Will you be using the short-term metric or long-term metric? I'll leave the answer to you, what you will say. Now we come to the process capability index calculation. This is a statistical formula and I will ask you to take my word for now until you go to a bit of deep statistical analysis and statistical course. Maybe I can bring a module for you and show you how this thing is calculated and derived. These two terms are synonymous with each other: LTL, UTL, LSL, USL, lower spec limit, upper spec limit. CPK is the minimum of either of these. Minimum of target, which is X minus upper spec limit or lower spec limit, divided by 3 sigma, because there is a 6 sigma between both the limits there. And minimum of these would be the capability of your system, not maximum, minimum. Minimum will show that how your system is performing. A capability index corresponding to 1 sigma, 2 sigma, 3, 4 and 5 and 6 is shown here. So anything which is less than 1 of CPK, that is to be thrown out of the system. Your system is not working fine, immediately address it. 1 is marginally accepted, and the more you go higher, the more it shows. CPK is the measure of how close to the target you are and how big is your spread. You remember the spread? More the spread, less is the standard deviation. Higher is the standard deviation. If the standard deviation is high, you have less numbers of sigmas there. So less is the spread, narrow is the standard deviation, more numbers of sigma, you get the good process. And it is centered, you get excellent target, which if you remember, I drew this I'll draw it once again for reiteration so that you can have a good understanding. This is voice of the customer. We go to another color. This is voice of the process. So if you are having this kind of configuration in your system performance, you relating the sigma levels to the number of DPMOs, defective part million per millions. This is something we spoke about in my first module as well. 1 sigma means you have a heavy number of parts defective per million. So this I don't need to go through it. This we have talked about earlier also. This graph shows these numbers show the improvement from the previous level. When you move from 1 sigma to 2 sigma, you improve by 55%. From 2 to 3, you improve by 78%, again compared to the previous level. From 3 to 4, you improve by 90%. 4 to 5, you improve by 96%. 5 to 6, you improve by 98%. You see, from onwards 4 sigma, every jump to the next sigma is nearly 100% improvement. That is multifold there. So regardless of the current process sigma level, a very significant improvement in quality will be realized just by 1 sigma improvement. That concludes my measure module. We are ready to go to the analyze module, and let's see how you understand the measure module and how you perform in this module. And we will be doing the further deep analysis of these variables, how these variables are related with each other, how they are performing, how they are affecting, is there a direct relationship or indirect relationship. That all comes into play in the analyze phase. Have a good day. See you next time.